So I'll do a talk about how to encrypt your data securely. And yes, I am using the default template in LibreOffice. So, if you ask most security, it appears I may have nudged it a little bit, and that has caused. It will fix itself in a few moments. Yeah. Okay. So, if you ask most security professionals, or a lot of them, for Linux, they would say Linux Unified Key Setup plus password-based key derivation function. Now, that's where you give it a password, and it applies a very, very hard hash to compute. Takes about a second of CPU time and about a gig of memory. The spec says 6 gigs, but realistically, that's a bit too much. So it takes a long time to unlock, but it's got a few problems. A, you've got to be there to actually type it in, and B, you've got to trust your bootloader kernel and initial RAM FS or initial RAM disk. Now, what are the bootloader kernel and initial RAM FS? I promise I'll get back to the password thing later. So to explain it, I've made a nice and easy to understand diagram where the firmware loads the bootloader, and the bootloader loads both the kernel and initial RAM disk. The kernel then runs the initial RAM disk, and the initial RAM disk and the kernel together have enough information to mount the root file system. This is the file system that you'll be using most of the time. So let's start off with the firmware. So the firmware is meant to be device specific, or at least platform specific, and it provides the drivers needed. Well, it provides drivers to load the kernel and initial RAM disk. It also loads the bootloader directly, and so typically in modern computers, particularly ones that run Windows, it uses UEFI. So it's a plug-in architecture where you register your device driver, and you register your device driver, and other things can request that device driver. As well as that, there's a more traditional struct-based mechanism for accessing critical drivers like the console and others, and being able to exit the boot services. It's a nice spec. I'd recommend reading it. Nice A-tier spec. So the firmware, its job is mainly to load the bootloader and have drivers. And the bootloader, it used to be much more significant when only 512 bytes were loaded from the disk initially, from the master boot record. That's then, the master boot record then loads the bootloader, and then the bootloader loads the whole system. But now with UEFI, we load the bootloader directly, and the bootloader can fairly simply, using the drivers, load the kernel and initial RAM disk. Now the Linux kernel, it's a monolithic design. It's also modular, but so it's got very good drivers. That's one of the main reasons why people actually use it to. People sometimes use it as a firmware replacement for that specific reason. It runs in ring 0 and it's very nice, but unfortunately, it's not typically able. Well, on some computers, it's not able to actually load the root file system directly. Maybe you've got disk encryption, which is somewhat the topic of this talk, or some other slightly odd setup, or you just don't have the drivers built into the Linux kernel, and it has to be loaded from somewhere. So, in order to fix all those issues, the bootloader, as well as loading the kernel, it loads in the initial RAM disk. It either contains a compressed file system image, which is the traditional initial RAM disk, or more recently, it's a compressed CPIO archive, because the developer didn't like tar, and it's loaded by the bootloader, because the bootloader, it can load the kernel, so it must be able to load the initial RAM disk, and it contains drivers for the drivers and software needed to mount the root file system, like BTRFS drivers, for instance. So now the diagram from earlier might make a bit more sense. But there's a significant problem with this as it stands at the moment, in that none of this is verified. So at pretty much every step of the process, you could potentially install a keylogger, for instance, and get the password from that password-based key derivation function, and just be able to decrypt the drive yourself. So people have known about this issue for ages. So what they've done is they created something called Secure Boot, which rejects unsigned images or images not signed with a valid key. But a problem is that it only applies to EFI applications, which are basically Windows portable executables, which are position independent. And from the diagram from earlier, whilst the bootloader and kernel can be EFI applications, the initial RAM disk is not an EFI application. So to fix that, we sort of wrap them both together into a unified kernel image, and that's just a program which, when run, loads the kernel from its own from its own segment table, and the initial RAM disk from its own segment table again, and then goes through the rest of the boot process as normal. Now, there's a few problems. Now, Secure Boot can be disabled. Maybe your firmware has a master password, or you don't want to set a password for risk of bricking the device. And also, signed images may still be vulnerable. It's hard to assess whether images should be trusted or not, but the closest thing we can do is assume that past images may be vulnerable and current images are not. So, with that, we still have the problem of where to store our keys. Because now, we still have to enter in a password, and someone may just swap out your laptop, for instance. So what we've got is something called the Trusted Platform module. It's secure storage, which, it's storage which is very secure, and it's also a security coprocessor. It's not great, the specification. It's split up into lots of parts, and and into lots of specifications, and even security professionals get it wrong quite often. So inside the Trusted Platform module, there are things called platform configuration registers, and those PCRs. There's only one real way to modify them, apart from resetting the whole computer, and that's to extend it, or extend as a noun, not as a verb. Now, that might seem a bit, that might seem a bit complicated, but what it says, what that's saying is, you take the old value of the platform configuration register, and you just tag on the new value to the end of it, and then you hash the whole thing. And what that's meant to do is it's meant to be able to implement a hash list, if you know what that is, where basically you can verify the order that the digests were plugged into it, as long as you know the final value and know all the digests. Now, it's supplemented with an event log, because if you don't know the what was pushed into it, hashes are pretty non-reversible, so you can't really, but you can't really get the value you put into it. So you've got to have an event log to be able to verify that, but to know what you've put into it. The first thing that's measured is the core root of trust for measurement. That's a part of your that's a program that's in your processor, which is the root of trust for measurement. And what it does is it measures itself, or just its version, and the rest of the EFI firmware, or UEFI firmware. They renamed EFI to UEFI, so if you see EFI, just know it's UEFI as well. So if we add that to our diagram from earlier, we have the core root of trust for measurement and the firmware. Now, platform configuration registers are nice, but we need to be able to say we only care about some of the stuff that's measured into them. So what's done instead is, there's actually 24 of them. I've included the ones that are relevant to firmware. There's also ones that are measured after the firmware has finished its job. This is from the UAPI group, and if we add those indexes into our diagram from earlier, you'll see that the firmware and the core root of trust for measurement are measured into PCR0, whilst the bootloader and universal kernel image are measured into PCR4, and the rootfs is unmeasured. There are some stuff to measure the rootfs, but that's not quite what we're going into now. So PCR0 records the firmware, 4 records the EFI applications which are loaded, and PCR7, which wasn't in the diagram from earlier, measures the secure boot state. And that's what keys are valid, what keys are valid to verify those keys, and what key is valid to verify the other key. So PCRs, so in order to actually, so what we can do is we can seal data so that it can only be decrypted if those PCRs are in a specific value. So now we need to know what value those PCRs are in. So PCR0, you can either get them from your system, or for some manufacturers like HP, they actually provide the value of the PCR, so you can verify it externally. PCR4, it has 4 events that we're interested in. Calling EFI application from boot option. That string itself is hashed and is extended, and is used to extend PCR4. Then we have a separator, which is 4 bytes of nothing, 4 null bytes, and then the bootloader, which it hashes the whole image and then stores it in, and then that's used to extend the PCRs, and then the unified kernel image, which is similar to the bootloader used to extend the configuration register. And PCR7 contains the secure boot variables. It can also be dependent on what applications are actually used, as it records what key what specific key was used to verify the image. So now we can seal secrets, now knowing what we should seal them to, but there's a slight problem in that the secrets aren't revocable yet. So we also have this problem of we don't have a place to store them yet, store the secrets yet. So the answers to both of those are NVRAM and NVRAM. On the Trusted Platform module, there's non-volatile RAM that can be used to store stuff like the sealed data, and it can also have a increment-only register, an increment-only thing, which can be used to revoke access to secrets. But in order to actually do that, we need policies which are signed. So they are a combination of requirements combined using and or. They are signed with a private key, and we can seal our secrets to the public key instead of sealing it directly to the PC platform configuration registers. So one of the policies we can use is policy NV, where the policy is only satisfied when the non-volatile RAM has a value within a specific index, for instance, 100 to 110. The way that it's meant to be used is that when you release a new version, you increment the second value, and when you want to revoke access to prior versions because they're insecure, you increment the first value to one more than what was accepted with the policy you assign to it. So now we're done, right? We've measured everything. We can make sure that our secrets can only be accessed by a secure, by an image that we know what it does, and we verified this. We made sure that our secrets can only be accessed by trusted images. But there's a slight problem in that with the password-based key derivation function from earlier, we can actually just log into another rootfs that's just masquerading to be that one, and then access the secrets. The solution to that is just disable the password. Now, so now for encryption. This encryption can't actually be used for disk encryption for various reasons, but I'm going to talk about char-char20, and it's a stream cipher, which means that what we do is we generate. We have our plain text at the top, and then our key in the middle, and then we have our thing at the bottom. But if we reuse that key, you would be able to tell the differences between the plain text. So we've got to generate a new key each time, which is what stream ciphers are there to do. They're pseudo-random number generators. And char-char20, it has it has a quarter round, which consists of the code up there. It's fairly easy to implement on 32-bit hardwares. A, B, C, and D are all 32-bit numbers. The three left arrows are rotation, and because of that, it makes sure that information, slight changes in the input propagate into massive changes in the output. But that's only a quarter round, so to create a full round, we do it in we use a 16 by 16 matrix of inputs, and we then apply the quarter round to each of the columns, and then we then do it to all the diagonals, and that gets us our random data after 20 of those rounds. So that's about it. Any questions?
more interested in like the encryption scheme
Yeah.
at the end. So for the random number generators, it's like they have the random number generator.
What did you say?
The XOR
Yeah, so this stuff up here is to generate the input for that XOR.
Oh.
So that it's unique for it's unique for every time we use XOR, so that you can't tell. Well, you can't tell the XOR the difference between inputs. Yeah. Okay.
Is that actually implemented on your laptop?
Not quite.
What business?
So with current technology, we can seal against the platform configuration registers, but we can't revoke access. Anything else, or?